In this video, I'll go through some examples of compositions of functions. So let's suppose we have a function g that takes some inputs and creates some outputs for g. Well, we could take those outputs for the function g and feed them into another function f. So those outputs for g will become inputs for f, and then they'll turn into outputs for f. So we've got two functions together, f operating on function g, but we could think of this whole process as a single process taking inputs into outputs. And so that composition of functions is written as f composed with g, and this composed with symbol is just like a small circle, so f on g. And it's important to get this the right way round. So f acting on g means you apply the function g first and then you apply the function f. If we did it the other way around, we would have g on f. So the g written first, and then the little circle symbol, and then the f. So to make that clear, let's go through some examples. So let's suppose the f function is x plus 2, and the g function is the square root of x. So what we're doing, if we're trying to figure out what f on g is, the composition of f on g, then we're applying the f function to the output of the g function, and the g function, the output is the square root of x. So if we think of the square root of x as the input for the f function, the f function says add 2 to the input, so this is going to be square root of x plus 2. Let's do it the other way around. Let's compose g with f. So now we're going to apply the g function to the output of the f function, and the output of the f function is x plus 2, and the g function takes x plus 2 as the input and takes the square root of that. So you can see in this example that it's important to get the functions the right way round, because f composed with g is square root of x plus 2, whereas the composition of g with f is the square root of x plus 2. So different functions. Let's do an example where it turns out that f on g and g on f are actually the same. So in the second example, f of x is x squared, g of x is 1 over x. So if we apply the function f to the output of function g, we'll have f acting on 1 over x, and the f function squares that, so 1 over x squared. We write it out in two steps here. So 1 over x squared is the same as, it's supposed to be an equal sign, 1 over x squared. Let's do it the other way around. Let's apply g to the output of the f function. The output of the f function is x squared, and the g function takes that x squared and takes the reciprocal of it, so 1 over x squared. So in this case, we've ended up with the same result for f on g as g on f. They're both the same. In the previous example, they were different. So that's just to show you that anything can happen. Let's do a slightly more complicated example. Let's do f of x equals 2 over x minus 3 and g of x equals 4 over x plus 1. So first of all, let's apply f to the output of the g function. The output of the g function is 4 over x plus 1. And the f function does 2 divided by 4 over x plus 1 minus 3. Okay, so we need to do a little bit of work here to simplify this. So let's first of all multiply through this fraction here by x plus 1 over x plus 1. So we'll have in the numerator 2 times x plus 1, and then in the denominator we'll have just 4 because the x plus 1 will cancel. So 2x plus 1 over 4, and then we didn't do anything to the minus 3 yet. And then there's a common factor of 2 in the numerator and the denominator here. So if we take that common factor out, we will just have x plus 1 over 2. And if we change the 3 into 6 over 2, we'll have x plus 1 over 2 minus 6 over 2. So we'll have x plus 1 minus 6. Simplify that to x minus 5 over 2. So that's the answer to the composition of f on g. And let's do the composition of g on f now. So let's see. So we're going to apply g to the output of f. The output of f is 2 over x minus 3. So the g function is 4 over the input plus 1. So 4 over, and the input now is 2 over x minus 3 and plus 1. Okay, let's do a little bit of algebra here to simplify this. So first of all, let's combine the minus 3 and the plus 1. So we'll have 4 over 2 over x minus 2. And then let's multiply through by x. So in the numerator we would have 4 times x, and in the denominator we'll have 2 minus 2x. So we'll have 4x and then 2 minus 2x, and then final step, we've got a common factor of 2 in the numerator and the denominator. So in the numerator, if we take out that common factor of 2, we'll have 2x in the numerator, and take out the common factor of 2 in the denominator, we'll have 1 minus x. So we've got 2x and 1 minus x. And that's the answer to the composition of g on f. So here's another example where f on g gives us one function that's different to doing the composition the other way around, g on f. And that's more typical, actually, is that we get different results here. It's unusual to get f on g and g on f be the same. So this was a special case, example 2. What about going the other way, going from a function and seeing if we can come up with two functions that if we compose them they would result in the given function? So let's have a look. What if we made f of x equal to square root of x plus 1, and then if we made g of x x squared minus 1. So then the composition of f on g would be, we're going to take the output of the g function, so x squared minus 1, and use that as the input for the f function. So we would have square root of x squared minus 1 plus 1, which is what we want, square root of x squared minus 1 plus 1. So those two functions work for f and g. Turns out they're not unique. We could also have, for the f function, square root of x minus 1 plus 1, and then just have x squared for the g function. Because now, if we take the output of the g function, which is x squared, and feed it as the input into the f function, we would have square root of x squared minus 1 plus 1, which is what we want. So there's an example of decomposing a function into an f and a g, so that when we compose them, they result in the given function.